Today we're going to talk about this equation right here. If you look at it from an algebraic point of view, you just have four variables. Algebra says you need three of the four, and you can figure out the fourth one. Should be pretty simple. But to match these variables, we need to know what they are. So first of all, delta G is Gibbs free energy. And since it's energy, we're looking at joules or kilojoules for units. And we'll come back to that in a second. Delta H is the change in enthalpy. Some people overpronounce this in college. So enthalpy is a measure of energy. This energy could be stored. It could be going from stored to kinetic. It's a change in energy total, not heat necessarily, but enthalpy. T is temperature, makes sense. And delta S is going to be a change in entropy. Entropy, again, overly pronounced, is a measure of disorder. The more disordered it is, the higher the entropy. Now that we got down what they are, we need to look at units because the units can definitely trip us up with this stuff. Delta H is usually measured in kilojoules because typically with these processes, most of them are chemical, but some can be physical. They're pretty large. A joule is not much. A joule equivalent in currency is 25 cents, which can't buy you much. The delta S is entropy, which is joules per mole Kelvin. So pretty much, and this is going to be per mole. So this is going to be joules per Kelvin. This is the actual temperature. Whenever you're measuring actual temperature, it must be in Kelvin. It can't be in Celsius. If you had a delta T, that can be in Celsius because the numeric value in delta T for Kelvin is the same value as delta T for Celsius, whereas 25 degrees Celsius numerically does not equal 298 Kelvin. Once you multiply Kelvin times joules per Kelvin, they cancel, but then you end up with kilojoules minus joules, and that doesn't work. So typically, we will convert the units for delta S from joules per Kelvin to kilojoules per Kelvin. So if you get a delta S of, say, 240 joules per Kelvin, we will convert that into kilojoules per Kelvin. That means that when we multiply it times the temperature, if it's standard temperature, it's 298, or it could be any other temperature they give us. The Kelvin will cancel, leaving you with kilojoules for T delta S. And then we have delta H, which is going to be in kilojoules, and we subtract those, which means delta G will be in kilojoules. However, in the future and in future chapters, we may have to use or come up with SI units, and SI units are going to be joules. We just have to make it all fit. If the answer is negative 225 kilojoules, and you put negative 225,000 joules, those are identical and it doesn't matter. Now, how do we come up with the value for delta S? Well, obviously, if they give us delta G, delta H, and T, we can solve for it. But typically, we have to solve for delta S separately. And the way you do that is simply last minus first. What we do is we look up a bunch of numbers and we will find values for each of the reactants and products, and we add up all the products, which is the sum of the products. You add them all up minus the sum of the reactants. Now they'll be listed like this. In this area, we have an appendix, and it says that, let's see here, the top we have delta HF, which is formation, and we have the delta GF, which is formation of Gibbs free energy, and we really seldom use that ever. And then we have S. Clearly states what the units are, joules per Kelvin mole. And here, these are kilojoules per mole. So we have to look at the units at the top, but they give us values. If we're looking up liquid bromine, we would find this number. If we look up gaseous bromine, we'd find this number. Being equal with the number of moles and temperature, gas particles have a lot higher entropy than liquids, and liquids have higher entropy than solids because they have more disorder in liquids than solids and a whole lot more disorder or chaos in gases. Probability they can be in more places than the liquid particles because they take up a larger space. Now, one thing I also want you to make sure you pay attention to is this is per mole. So if you had a coefficient in front of the bromine, like the liquid bromine of like 3 bromines in your balanced equation, then you would multiply this number times 3 because the balanced equation is saying you have a 3 coefficient means 3 moles. So 3 moles would be 3 times the value. Only way you really can calculate delta S as opposed to knowing the other 3 variables in this equation. However, to figure out delta H, and there's a lot of different ways we could do this. One, we could be given heats of formation in which we do the same thing. It's last minus first. And if the coefficient is the 3, we multiply it by 3. The only deal with this is if it's something in the equation that's an elemental form, the heat of formation is 0. The reason is heat of formation is the energy change required to build a compound up from elemental forms, which means it takes no energy to build an element from the element. If we're trying to solve for delta H and we're given a different set of data, let's say bond energy here in red, then we do almost the same thing, except this is this is first minus last. It's the only time in this junior year that you do first minus last. There's one more time in which we can use heats of combustion, but we don't do this for the junior year. So this is the only time we do first minus last. Do the same thing. It'll be bond energies. All the bond energies are positive because it is defined as the energy required, positive, to separate a bond into the single elements. A bond is a stable entity, so to move those away from each other would always require energy. Anyway, to get the sign right on delta H, we actually have to do first minus last. Same thing, if you had 3 moles of a compound, you might think you need to multiply it by 3. But if it's something like water, well, water has 2 OH bonds, and therefore, if you had a coefficient of 3, there'd be 2 in the compound, 3 moles, and therefore you'd multiply it by 6. So you do have to take into account that. But that's another way we could come up with delta H. A third way to come up with delta H is using coffee cup calorimeter. We don't do bomb calorimeters in IB, so coffee cup calorimeter in which water or the solution, we get the mass of it. If it's water or an aqueous solution, we assume it has properties of water or it will be given that. We'll have a final and initial temperature. We can solve for that. And therefore, we can calculate for Q. Q is heat. And the heat going in or out of the water or solution is based on the separate reaction. So if we end up with negative 4,200 joules for Q, then we would say delta H would equal to a positive 4.2 kilojoules. Typically you have to change it to kilojoules to match the T delta S. You just got to make it match one way or the other. However, the process of this water or solution absorbing or giving off energy is going to be the opposite of what happens with the process that drives it. So if this on the left absorbs energy, that's a positive, and it must get it from the right side, which means it gives it up. If it gives off energy from the solution, it's going to go into the process, which is why it's always a negative sign. So that's another way we could solve for delta H. So if we're doing straight calculations, that's kind of how we can come up with it. If it's standard conditions, temperature is 25 Celsius or 298, which we have to use the 298. If it's at a different temperature, then they would need to tell us the temperature. Problem is sometimes they give us more concept problems that are math driven, but not actually math calculations. We do well with the calculations, but the concept parts are kind of tough. So they can give us this reaction here, and they can say, under what conditions will this be spontaneous? And when they say, under what conditions will this be spontaneous, they mean, will delta G be negative? That's spontaneous. Delta G positive is non-spontaneous or technically spontaneous in the other direction. Well, what do we want for this to be negative? Well, we got to incorporate delta H, T is always positive, delta S, and so we have 3 components, but really this is boiled down to 2 components. So let's look at this. If this was a combustion reaction, say methane plus oxygen yields carbon dioxide and water, we recognize this combustion, we know delta H is negative. That is one of the signs you just have to know. Really none other. Next year we'll need to know neutralization, but this year it's just delta H is negative for combustions. Heat's given off. In this case, they give us delta H and it's negative. And this really isn't going to be a calculation problem. If we did, that would be fine. We have one of the 3 components. So now we need delta S, and what we're looking for is the sign for delta S. So let's first of all look at the phases. Phases often dictate it, but these are all the same phase. They're all gases, and therefore things that are the same can't cause differences. So since they're all gases, the phase has nothing to do with the change in entropy. But if you look at the left side, we have 2 plus 1, that's 3 moles. And you look on the right side, we have 2 moles. That means that you have fewer particles. And if you did last minus first, you get 2 minus 3. That equals to a negative value. So delta H is negative because of this sign. Minus T delta S. So this is negative. And a minus minus a minus equals 2. And the answer is it depends on the magnitude. I like to change these 2 signs so that it makes more sense to me. A minus minus is a plus. And so what we do is delta H is negative and plus a positive. So when will this be negative? When will this equation be negative? And that is when the positive guy is smaller than the negative guy in absolute value. We can't change the size of delta H or delta S, but we can change the size of the temperature. So how do we make T delta S? How do we make T delta S small? We're going to reduce the temperature. So this will be spontaneous at low temperatures. Does that mean it's cold? No, it just means if you keep reducing the temperature, at some point, the positive delta G will flip to a negative delta G, and you'll have a spontaneous reaction. Hope this helped. We'll talk to you later.